All right, it's 3 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, good. See some nods. Hopefully everyone's doing good. Through this like kind of fluid mechanics boot camp that we're going through. It's a lot of fluids. All right, so today we're wrapping up our lecture notes on fluid statics. So we have two main topics today. So the first topic is basically how to compute hydrostatic forces on surfaces. So we started this in the last 5 minutes on yesterday, but we're going to finish that today. I have a couple examples for that. That's probably going to be the trickiest part that we're going to do in this section. So we're going to spend, a decent amount of time, at the very least the first half and maybe half of the second half too. And then for the last part of the class, we're going to be going over buoyancy. Buoyancy is not too difficult. So I think probably we'll only spend 30-45 minutes on buoyancy. Okay. All right, and so just as a reminder, homework 1 is due tomorrow. So as of right now, you should be able to do problems 1 through 3, or at least problems 2 and 3. And then for problem 4 and 5 and the conceptual problems and problem 1, you should be able to do them after today. Okay. So basically the way I've set up the homework is that there's basically a problem for every main, I would say, type of problem or every main kind of topic that's there, along with just some conceptual problems that kind of tie together all the concepts that we do over. Okay. So today was the last office hours that I had before the end of the week. That was, earlier before class 1:30 to 2:30. But if you do have questions on the homework before it's due tomorrow night, you can definitely send me an email. So I don't have office hours tomorrow, but I will be available over email. So I'll be working on other stuff tomorrow, but I'll be at my computer so I can answer you guys' email. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's get started. Okay. So let's go ahead and pick up where we left off. So what we were discussing yesterday was hydrostatic forces on planar surfaces. Okay. So basically, the idea with this section is that, whenever you have an object or whenever you have any kind of surface that's submerged in a liquid, there's going to be hydrostatic forces that develop. Right? Okay. All right. So the situation's like this. So we have a tub of fluid here, right? Let's say that we submerge an object. Okay. The object doesn't have to have any particular shape, at least not now, right? So we just have a potato-looking thing, right? And so we know just based on what we discussed yesterday that this object, just by nature of being within a fluid, is going to have pressure applied, right? Right. So the main thing that we talked about yesterday was that, as you get deeper and deeper within a fluid, more and more pressure is going to develop because all the fluid at the bottom has to essentially support the weight of all the fluid above. Okay. And then that pressure gets exerted on any solid object or any surface that gets applied, that gets submerged within that fluid as well. Okay. So for the entirety of yesterday, we all we talked about was, how do we compute that pressure, based on depth, and we talked about applications like manometry and so on and so forth. Okay. So today, we're starting with kind of the very next step where, now that we know that these pressures are being developed, how do we go from those pressures to an actual applied force, right? Because if we can convert that pressure to an applied force, we can actually start to do some very interesting type of problems with that. anytime you have a pressure that's acting on a surface, there's going to be a force that results. Okay. Okay. And then, like we mentioned last time as well, if you have a horizontal surface where every single part of your surface is at the same height, it's pretty straightforward. You basically just compute the height or the depth of where your object is. You multiply that by the specific weight of the fluid. That gives you your pressure. Then you multiply your pressure by the area. Right? So that's fine. The complication occurs when you have objects that have, any kind of height associated with them. Okay? Because if you think about it, right? So if you have an object that has any kind of non-insignificant size, if you compare the top of the object to the bottom of the object, right? Because the top of the object and the bottom of the object are at different heights or different depths within the fluid, they're going to be experiencing different pressures. Okay? And so the main question that we're going to reconcile first today is, how do we, how do we account for that? How do we account for the fact that, if our object has any kind of significant size or depth, right? How do we account for that in terms of computing the forces that develop on a type of surface like this? Okay. Now we aren't going to be doing a complex surface like this. So for an arbitrary surface like a potato, it is a bit complicated. So we are going to simplify things a bit. So we're going to focus on just planar surfaces, and all that really means that our surface is completely flat. Okay. Now that surface may be horizontal, like we talked about last time. It may be vertical, or it may be inclined. All right. So we're looking at a situation like this. We have our fluid here. We have our planar surface. Right, we know that pressure force is going to develop, and that's going to produce a distributed force. It's a little bit hard to tell. I kind of tried to draw it a little bit more accurately, where the parts of the surface that are near the bottom of the tank are experiencing greater force, but there's greater pressure. So there's kind of a slight incline, although I think I didn't do a very good job of it, but I didn't want to emphasize it too much. Okay. So how do we basically deal with situations like this? Okay, because ultimately what we want to do, and you'll see this in the two examples that we're going to do in this area, that ultimately we're going to take situations like this and turn it into a static equilibrium problem. Okay. So I think for the most part, I know it's not an explicit prerequisite for this class, but I think at this point most of you have probably taken statics. So in a static equilibrium problem, basically we're going to be taking a sum of all the forces in every direction and setting them equal to zero. Okay, and what that's going to do is that's going to give us a system of equations that we can solve for to solve for any kind of manner of unknowns. Okay, so both the examples that you're going to see today are going to be like that. Problem 4 on the homework is exactly like that as well, right? So essentially you're going to be solving for something like this. Okay. All right, so that's kind of the setup. That's kind of the motivation of kind of what we are going to do. Okay. Any questions on this so far? Okay. All right. So let's go ahead and get started. Okay. So in order to convert this into a static equilibrium problem, the main difficulty that we want to do, or that kind of presents us, is that, a pressure is essentially a distributed force, right? That's just kind of how pressures work, right? So essentially, they're a force that's distributed along a surface or over an area. Okay. Now that's good conceptually, or conceptually that's kind of good to think about. But in terms of calculations and in terms of actually working with that, distributed forces are actually a little bit harder to work with. Okay. So the first thing we're going to need to do is we need to take this distributed force and turn it into a resultant force. So a resultant force being a single force vector that has a direction, magnitude, and location, where the net effect of that resultant force is exactly the same as the distributed force. Okay. All right, so essentially, we're going to do this. And so we have our surface like this, right? And normally we have a pressure force that's being applied onto it like this, right? So this right here is the distributed force. So what we want to do is we want to convert this based on our knowledge of hydrostatics and based on kind of the derivations that we're going to do into a situation like this where we have just a single force vector, which we'll call FR, which is our resultant force. Okay. So FR, we know its direction, we know its magnitude, and we know its location. Okay. Because now we can just take that a single force vector and then do a simple just summation of the forces or summation of the moments from there. Okay. But to go from the distributed force to the resultant force, a little bit tricky, a little bit complicated just because we have that varying pressure, but that's kind of what we want to do with this part. Okay. Okay. So in order to get the resultant force, we need to determine three things about that resultant force vector. All right, so just like any vector, we need to know its direction. We need to know where it's pointing. 2, we need to know its magnitude. Okay. And 3, we need to know its location. Right, so basically where it's acting, right? So 1 and 2, direction and magnitude, that's basically all you need to do a summation of forces. But a lot of times in these problems, you'll see, and the two examples that we're going to do, we also need its location, just because we're going to also sum the moments around a particular location. Okay. And so we need to know exactly where this force is acting so we can compute the moment arm for the force. Okay, so today will be a little bit of a refresher of statics. Hopefully it's not too traumatic. Statics, I know probably is probably the first engineering course that a lot of people take, and it can be a little bit intense, but hopefully today will be good memories for them. Okay, so let's just go down this list. And so I've listed these in kind of order of complexity as well. So direction is probably the easiest to determine, and location is going to be the parts. Okay. Okay, so let's talk direction first. Okay, so the direction just tells you, which way or which angle the force is pointing. So that's very easy to determine. Okay. And so, because we know, and we discussed this last time that, a pressure force, just by its nature, is always going to be perpendicular, applied perpendicular to whatever surface that is acting on. And so whichever direction your surface is pointing in, you just make a right angle on top of the surface, and then you draw your resultant vector. That's the direction. Okay. So direction is quite, quite simple. Okay. Now you do have to probably do a little bit of trigonometry, and you'll see that kind of in the first example. But just if you always remember just that pressure force is always perpendicular, there should be no parallel component of the pressure force on a surface. And as long as you draw it out, most of the time you're going to be okay. So pressure, so direction, done. Okay, so we don't need to kind of discuss that anymore. Okay, next thing we're going to discuss is the magnitude. Okay, so magnitude is a little bit tricky because remember, if you have any kind of surface that you have different parts existing at different depths, different parts of your surface are going to be experiencing different pressure forces. Right, so that was kind of the main motivating thing that we kind of talked about today. Okay. Okay, so let me just, to illustrate this, let me just go ahead and draw our surface again. Right, so let's say we have an arbitrary inclined surface. So the surface is flat, okay, but it's inclined. And so that means, the top of this surface and the bottom of the surface are going to be experiencing different pressures because they're at different depths. Okay. Okay. So how do we reconcile this, right? So there is a derivation that I have in the notes, but I think it's probably a little bit easier just to explain it qualitatively. Okay. All right. So we have the top of the surface here, and let's say the top is at a depth of h1, right? Where h1 is the depth from the surface down to there, okay? Or excuse me, from the bottom of the tank up to the top. And the bottom is at a depth h2. Okay. All right, we know that the pressure at the bottom, H2, is going to be greater. Right, versus the pressure at the top, which is less because it's at a less of a depth. Okay? So we know P, so if we denote this P2 and P1, right, we know that P2 is going to be greater than P1. Okay. In fact, we can actually plug in for our equation for the pressure that they're going to be experiencing, right? So P2, if we plug in, P2 is going to be rho times gravity times H2, and P1 is going to be rho times gravity times H1. Okay. But then in writing this, we kind of notice something about this formula, or maybe you might have noticed this already too, right? Where if you look at our pressure formula, right? Whenever you're looking at kind of these scientific formulas or mathematical formulas, it always helps to see or to take a look in terms of how does your quantity or how does your result depend on your variables. Okay? So we know from last time that the pressure that develops in the fluid depends on its depth, right? That's what I kind of just highlighted there. But if you look at how that height or that depth appears in that equation, you'll see that it appears with an exponent of 1. Okay. So it's not written here just because, usually when things have an exponent of 1, we just ignore it. But we can say that both of these have an exponent of 1. Okay. All right. So when quantities like this or when variables in an equation have an exponent of 1, we say that the quantity has a linear scale. Okay. So if the equation were instead, rho times g times h squared, right? H squared would mean that the pressure scales quadratically with the height. Okay. So we'll see different examples of different scalings later in the class, but I wanted to highlight this one here just because it's relatively simple. Okay. So linear scaling is very nice because linear scaling lets us do a lot of really a lot of assumptions and a lot of simplifications. Okay. Okay. And so basically, when you have linear scaling, what you can assume then is that the difference in pressure, right? Because if you kind of travel along the surface here, right? Let's say you go from the bottom up to the top, right? So as you travel along that surface, then your pressure is going to be varying linearly between them, right? And so if you make a graph, where on the horizontal axis we have the distance along the surface, okay? And on the vertical axis here we have pressure, right? And let's say we're traveling from the bottom to the top, and so let's say that we have P2 up here, which we know is greater, and P1 is down here, right? Okay. So with linear scaling, we know that the path from P2 to P1 is going to be linear. Okay? Linear means that we just have a straight line. So why is a straight line significant here? Well, on a straight line like this, it's very easy to determine the midpoint. Okay? And then at the midpoint, you can compute the pressure. Right? And if everything is linear, that means the pressure at the midpoint of the surface is equal to the average of the pressure at the bottom and the top. Right, now that's very significant because now that we can identify a very clear average, right? We know the average pressure, and in fact, that average pressure is occurring right at the midpoint of your surface. That tells us something. That tells us a way that we can simplify this. Okay. So what that tells us is that if we want to compute the magnitude of the pressure force on a surface, the easiest way that we can compute it is if we take the centroid of our surface, okay, take that to be the average depth of our surface, and then compute the pressure from there. Okay? And then that average pressure can be used to compute the magnitude of the force, because we can say that that's the average pressure that your surface is experiencing. Okay? Therefore, the magnitude of the pressure force is equal to the pressure at the midpoint, multiplied by the area of the surface. Okay? Right, where pressure at the midpoint is just the product of the density of the fluid, acceleration due to gravity, and the height or the depth. Excuse me, I should be more clear. The depth of the depth of where the centroid is. And I know I keep flip-flopping this, but I was just looking at the example we're doing later. When I say depth of the centroid, I mean as measured from the free surface. I apologize. I know I've been confusing whether you should measure the height from the bottom or the top. In this case, we're measuring the depth from the top of the fluid. Okay, good. All right, so there's a bit more of a mathematical derivation in the notes. It involves a computation of moments, but maybe I was thinking maybe the qualitative description might have been a little bit easier, but that also kind of took a while a little bit too. But hopefully it's clear. Okay. All right, any questions on magnitude of the hydrostatic pressure force? Okay, good. All right, so that takes care of the magnitude. So last thing we have to determine is the location of this force. All right, so this gets a little bit tricky, right? And so there's not really a great kind of qualitative derivation for this. So we do have to kind of do this from kind of the mathematical point of view. But let me kind of motivate why this is important. Okay, so it's a little bit misleading because we had just gotten done talking about the magnitude of the force, and we can say that we compute the magnitude based on where the centroid is. Okay. So it's very tempting, right? It's very tempting to say that, if the magnitude is based on the centroid, it's very tempting to say the location of the force should be at the centroid as well, right? But that's not necessarily the case. So even though So even though we compute the magnitude of the force from the centroid, the location of the hydrostatic force is actually going to be slightly below or at a slightly lower depth from the centroid because of how the pressure forces scale with the depth. Center of pressure. Yeah, it is actually. Yeah. So yeah, so the name of this location is the center of pressure. But but we need to kind of motivate in the equation in terms of how to get. Okay. And remember the reason for this, the reason that the center of pressure is slightly below is the fact that the pressure is greater at greater depths. Okay. So if you have a surface like this, right, its centroid will be something like right here. Okay. So let's say this right here is the centroid. So the location of the hydrostatic force is actually going to be slightly below. Probably going to be something like that. Okay. So what you're going to see is that the equation that we're going to derive here is that we're going to we're going to base this location based off the centroid, but we are going to add a slight adjustment to it. Okay. I think that's kind of the easiest way to think about it. And so, when you're locating these hydrostatic forces, first start from where the centroid is, and then, we're going to add this little adjustment or this little offset based on the fact that our pressure force is greater at greater depths. Okay. Okay. But the question, of course, is, how do we obtain a formula for that adjustment? Okay. So to do this, we do need to make use of a moment formula. Okay, so the derivation kind of goes like this. And so let's go ahead and take a generic case. Okay. So let's consider a tiny surface that's kind of submerged within a fluid. So we have a situation like this, and so we have a fluid. This. Okay. Let's say that we have a tiny surface like right here. Okay. So the reason is, the reason we're calling it a tiny surface is that we are going to be doing some integrals. Okay. So let's say that this tiny surface has an area dA. Okay. It's at a depth h. Right, so we know its depth. Okay. And just so that we can make this equation kind of general in terms of surfaces that are at an incline, we're going to assume that we have some kind of axis here, just like that, where this axis is angled at a certain angle theta. And so this is just to account for the fact that we can have surfaces that are inclined at any angle. So now our formula will be general enough to work for horizontal surfaces, vertical surfaces, and kind of everything in between. Right? And then based on that incline there, we also know this length here, and we'll call that y. Okay. So that y is the length from the surface to our tiny area, but not the vertical distance, but the kind of this inclined distance. Okay. Okay. All right. So based on this geometry here, we can express the depth of this force here, or the depth of the surface, in terms of watts. Right, so we just use a little bit of trigonometry. We can say that h here is equal to, if we consider h to be kind of the vertical surface of a right triangle, that has that angle theta, and y there is the hypotenuse. We can say that h is equal to y times sine of theta. Right, and then we can use this to express the magnitude of the force. Okay. All right, and so using our equation, here the concept of centroid doesn't really matter because it's a tiny surface, and so the entire surface is at the same depth. So we can say that dF, or the force on that tiny surface, is equal to rho, density of fluid times gravity, times y sine theta, which is the depth multiplied by dA, the area. So basically just taking our hydrostatic equation, rho times gravity times the depth, multiplied by the area, and that's how we get our force. Okay. Okay. So now that we kind of set up our little differential element here, we can use this to compute the location of the resultant force. Okay. Because the idea here is that, if we take our resultant force and we multiply it by its resultant location, this should give us the exact same moment as our distributed force that's distributed over the surface. Okay. So this is pretty typical, maybe you've seen this already in your statics course, but whenever you're computing something about a resultant, basically you compute what the resultant would be, and you compute what the effect of the distributed force would be. You set them equal to each other, and then you can use that to solve for something for the result. Okay, so that statement right there, it's kind of a wordy statement. It basically looks like the following. Okay. So on the left-hand side of this equation here, we're going to have an integral expression that computes the net moment from our distributed force across an entire surface. Okay. So we're going to have integral y times df. Okay. So this right here is the net moment, right, from a distributed pressure force. Okay. basically we're taking the force contribution from that tiny surface and then just adding up all contribution from an entire surface, okay? So in that situation, we're assuming our tiny surface is just a tiny part of a larger surface, okay? We're adding them all up, that's why we're integrating. And so this is equal to the magnitude of the resultant force, which we had just computed, multiplied by the location of the resultant force. So this FR here, this is the magnitude of the resultant force. And YR here, this is the location of the resultant force, which is what we want in the end. All right, so these two things should be equal. If we're going to be representing our distributed force with the resultant, then they should have the same net effect. Okay, so essentially we're going to basically plug in everything in this formula. We're going to have to evaluate this integral there, and we're going to get we're going to get an equation for YR. Okay, what you're going to see is that the result is less intimidating than you think it's going to be. Okay, it's going to go back kind of what we kind of first thought here, which is just, our location is just going to be the location of the centroid plus an adjustment. Okay. It may not seem like it, but that's what we're going to get from this equation. All right, any questions on this so far? Okay, all right, good. All right, so let's go ahead and work in. All right, so let's go ahead and plug in for df, just because we already came up with an expression for that. We're going to plug that in for there. Okay. All right. And then let's go ahead and plug in for FR as well, because that's what we got from before. Okay, so we plug in for those two, we get integral of y. We plug in for df, and so df is rho times g times y times sine theta times dA. Okay. This is equal to, so let's go ahead and plug in for the magnitude of the resultant force, which we already know. So the magnitude of the resultant force is rho times g times the depth of the centroid, okay, times A multiplied by YR. So for FR here, we just plug in our expression from up front. Okay. One more thing we're going to substitute here, just to make sure everything is in terms of y's here. Right? Let's plug in for HC. Okay. So based on the geometry that we're working with this kind of a triangle type geometry here, right? And we know the relationship between H and Y, we can say that HC here is YC multiplied by sine theta. Or YC is the location of the centroid, but instead of being measured as the vertical drop distance from the top of from the free surface, we're measuring it along that incline. All right, so thankfully, with this expression here, a lot of this is going to cancel out, right? Because a lot of these quantities are constants that don't depend on the area. Okay. All right, so first thing right away, what we see is that on both sides of the equation, we have a rho, we have a gravity, and after we plug in for HC, we have a sine theta. All of those are going to cancel out. Very satisfying to have things cancel out like that. Okay. We have two y's that are going to be multiplied by each other in the integral. So on the left-hand side here, we have integral of y squared dA. That right there is a very special integral that you're going to see in a second. And on the right-hand side here, we have the product of yc times a times yr. Okay. All right. So let's talk about this integral here. So thankfully, we're not actually going to evaluate this integral because we were able to get it into a very special form. So this integral right here is an integral for what's called the moment of inertia of your surface. You never thought you'd see moment of inertia again after your statics class, but here it is. It always shows up in the place you least expect. Okay. Now, more specifically, there's no such thing as a general moment of inertia. When you talk about moment of inertia, you're always talking about, where is this with respect to, right? Because moment of inertia is all about kind of angular motion, rotation, things like that. Okay, so you would have to have an axis, and so this moment of inertia in specifically is with respect to the free surface, because that's where we're measuring everything from. Okay. So that's good. That's fine, right? That's just how the equation kind of ended up. But in this form right here, this is kind of really inconvenient because typically speaking, whenever you're computing moments of inertia, you never really want to be computing this integral because it's even though I have it as a single integral here, technically we're integrating over an area, right? So there's dA, so this is a double integral. So you almost never want to be computing this integral by hand. So usually when you compute moment of inertias, if you kind of recall from your previous classes, most of the times we want to be looking this up in a table. Right? Because if you recall, from your previous class, different cross-sectional shapes, whether you have a square, a rectangle, a circle, an I-beam, an L-beam, right? They all have different formulas for moment of inertia. And then you never really want to derive those equations. You'd rather just kind of look them up in a table. That's just kind of how things are kind of more practical. Okay. The problem though is that you can look up a table, right, and the table will have just a variety of different shapes and their moments of inertia, but a table will almost always produce your moment of inertias with respect to the central. So that's kind of a problem, right? Because we want to use the tables, but in our formula here for YR, we have moment of inertia, but it's not from the centroid, okay? All right, so thankfully there's a fix for this, okay? And the fix for this is our parallel axis theorem, okay? Because with the parallel axis theorem, we can basically take any moment of inertia, express it in terms of the moment of inertia of our centroid, plus kind of that offset factor, okay? Oh, sure. Yes. Yeah, so HC is equal to YC times sine theta. Yeah. Or are you looking for this one right here? H is equal to Y times sine theta. Good. Yep. Okay. All right. So last step in this derivation, I know kind of a lot of this ending part here was just kind of me talking, but we're going to use parallel axis theorem to plug in for that moment of inertia. Okay, so under the parallel axis theorem, okay, what we can say is that the integral of y squared dA is equal to, okay, remember integral of y squared dA, this is a moment of inertia with respect to the free surface. Okay. I'm using the acronym here, WRT. WRT stands for with respect to. Okay. Okay, so this is equal to I x c. Okay. So I'm using the symbol I here to refer to the moment of inertia. So I x c here, this is the moment of inertia with respect to the centroid of our surface. Right? And so that's always nice because this is tabulated. So this is something we can look up pretty easily. Plus, we have our offset factor. So our offset factor is A, which is the area of our surface, times YC squared. Or YC is the location of our centroid, okay? From the previous axis, which is from the free surface. So this AYC squared here, this is our offset factor. All right, we're almost done, I promise. And then we'll do an example, and then we'll go to break. All right, so let's take this expression and let's plug it in. Okay, so we're going to plug it into our expression up here. Okay. And then finally, we'll be able to get a practical expression for YR, which is the location of our center of pressure. Okay, so let's plug this in. Okay, so we plug that in, we get I xc plus AYC squared is equal to, okay, is equal to YC times A times YR. Right, so that equation at the bottom of the screen, all I did was I plugged in our parallel axis theorem for the left-hand side of our expression. Okay. Now we can take this. Now this is a very nice compact equation. Let's go ahead and solve this for YR. All right, and so we do that. We get YR is equal to IXC, moment of inertia with respect to the centroid, divided by AYC plus, we have AYC squared divided by AYC, and so the AYCs are going to cancel out. We just get YC. Okay, so this formula here, this is our location of our resultant force, otherwise known as our center of pressure. All right, good. All right, so now we have all three components of our resultant force. We know its direction, we have a formula for its magnitude, and we just finally derived a formula for the center of pressure or its location. Okay, so we're going to apply all three of these in our next example. So the next example we're going to do is essentially a very classical statics type problem. We're going to be summing up forces, or we're going to be summing up moments setting equal to 0. But we're going to need all three of these equations in order to complete that equation. Okay. Right. So when you're doing these kind of problems on hydrostatic forces on surfaces, think of them as statics problems, just with a couple extra steps that you need to use to compute the forces. Okay. All right. Any questions on this before we jump into that example? Okay. All right. So let's go ahead and do an example here. Okay. So for this example, let's consider a circular gate submerged in water. Okay, so we have a situation, we have a gate that's underwater, and maybe it's blocking, maybe it's like a sewage drain or something. Okay. All right, so we have a situation, we have a pool of water, right? So this here is our free surface. Okay. And then inside the water, we have a circular gate. You're probably thinking that's not a circle, that's a rectangle. Well, we're looking at the circular gate from the side, right? And so this right here is the side view. But if you look at it from the front view, so let's say you're looking at it straight on from the gate, it's a circle. Let me make it a little bit smaller just to kind of make it a bit easier to see. Okay. I think that's the other thing that's confusing about these problems too, is that we're always have to look at them from the side because we have to see how deep it is. But there's a frontal view that shows you the shape of whatever surface it's looking. Okay. So this gate here is part of a larger mechanism, right? So let's say that this gate is kind of blocking a channel like this. Okay. The gate is hinged at its centroid, right? So there's a hinge that kind of goes right through the middle, just like that. So that means this gate can normally kind of rotate around that hinge. So we're going to rotate either clockwise or counterclockwise from here. Okay. There's a little stopper here. Okay. So there's kind of a piece of material here that's kind of blocking the gate, just to make sure it doesn't just open on its own. And because the gate here, and because this circular gate is submerged in water, it's going to be subjected to hydrostatic forces. Okay. Okay, so let's put some numbers on this. And so let's say that the depth of the centroid, we kind of erase this just to make things a bit easier. Okay. I apologize, I'm moving the location. Okay. All right, so our hinge is still in the same place. Let's say the depth of the hinge is 10 meters. All right, and since our hinge is conveniently at the centroid, we can say that the depth of the centroid HC is 10 meters. Okay. The incline of this gate here we'll say 60 degrees. Okay. And let's say the gate itself has a diameter of 4 meters. So this diameter here is 4 meters. Okay. And I'll draw that on the front view just so you can see it. Okay. All right, so with this situation, let's go ahead and see what we need to solve for. All right. So first, let's compute. Okay. Very simply, we have a surface here. We have this gate, the circular gate. Let's first compute the magnitude and location of the resultant pressure force. Right? So that's just going to be a kind of a straight application of the formulas that we just discussed. Okay. And then part B, so I'm going to modify part B a little bit. So if you're following along with the lecture notes that's posted online, I'm going to try to change part B. But for part B, we're going to compute the reaction force at the stopper that's required to prevent this gate from moving. Okay, so we're going to do a sum of the moments. Okay. All right, so this is a pretty typical problem in this run. Okay, so we have an inclined surface. We know the incline direction, so the incline is 60 degrees. Sorry, I had it cut off for a little bit. Okay. We know the size and shape of our surface. We have a circular surface with a diameter of 4 meters. We know its depth. The depth of its centroid is 10 meters, and so we're computing just basic kind of quantities from here. Okay. Any questions on the problem setup? Okay. All right, so let's go ahead and start solving it. Okay, so first thing, let's compute the magnitude of the pressure force. So for that, that's going to be our formula for FR, right? And remember, the way we compute this is we compute the depth of the centroid. We compute the pressure at the depth multiplied by the area. So it's going to be rho times G times the depth of the centroid multiplied by A. Okay. Okay. All right, so we're given everything here. The only thing we just have to moderately compute is just the area of a circle, which is not that bad. But we do have to look up the liquid that we're using, which is water. Okay. Right. So for water, right, I think the thing that I kind of conveniently remember is that the density of water, remember, is about 1,000 kilograms per meter cubed. I know technically it's 999, but 1,000 is just more convenient. Okay. So we'll round up. Okay. All right, we know that gravity is 9.8. We know HC. HC was given to us in the problem. The depth of the centroid is 10 meters. Okay. In the area, right? So the area here is just going to be the area of a circle. Okay. So we're given the diameter. So area of a circle from the diameter is pi over 4 times diameter squared. Okay? Or if you want to just do a radius is diameter divided by 2, and you just do pi times the radius, get you the exact same thing. Okay. All right, so we plug all of this in. Okay, so this is just a very simple plug and chug. We get FR is equal to 1,231,504 newtons. All right, so magnitude of forces, always pretty straightforward. Okay. Okay, so now let's compute the location. Or in other words, let's compute its location of the center of pressure. So let's go ahead and use our formula from before that we had just finished deriving up here. Okay. We have YR is equal to IXC, which is the moment of inertia of the center of the circle based on its centroid. So we're going to look that up in a table. Divided by YC times A plus YC. Okay. All right, so thankfully for area, we already know that. We just computed it. I know I didn't write its value, but we can compute that easily. Okay. Let's start with the moment of inertia. So the moment of inertia of a circle, right? So remember, so this would be something you would look up in a table. Yeah, it's pi over 4R. Yeah. Right, so if you look this up in a table, so for a circle, based on its centroid, the moment of inertia with respect to the centroid is equal to pi over 4 times radius to the 4th. Okay. All right, good. Other thing that we have to compute here is YC. Okay. So be careful here because, remember, there's a difference between HC and YC, where HC is just the straight depth of the centroid. So that's just the vertical drop distance between the free surface and the centroid. YC specifically is the distance along the incline to get to your centroid. Okay. So once again, we're going to use our, use our kind of triangle here. Right? Because remember, we have this relationship where this is HC, that's the vertical distance. We have YC, which is this distance just like this. Okay. And the angle that we have here is this one right here. Right, so that's kind of the right triangle that we're working with for our situation. This means that YC is equal to HC divided by sine theta. Right, so we plug that in, we get YC is equal to 11.55 meters. Okay, because we know HC is 10 meters, right? And theta here is 60 degrees. Let's go ahead and plug in our for our moment of inertia. Now be careful with the moment of inertia. Remember, this is radius, and so don't plug in the diameter to this equation. Okay. And so we plug in our radius of 2 meters, and what we get is a moment of inertia of 12.57 meters to the fourth. Okay. All right, and so we plug all that in. So we know YC, we know the moment of inertia, we know the area. We plug all that in, we get YR is equal to 11.64 meters. So not that different actually. And so if you compare this to YC, right, it's not that different. YC is 11.55 meters. The center of pressure here is 11.64 meters. So it's only about a difference of not even 0.1, less than 0.09 meters. Okay. So if we draw this out, here is our circular gate that we're looking from the inside. Okay. We have our centroid, right? Right. So if we go up from the free surface, okay, going from the free surface to the centroid along that inclined surface, we know that YC is 11.55 meters. The center of pressure, though, is slightly past that, right? And so if we were to draw the resultant force, right? So the resultant force would be something like this. This location, with respect to the free surface, is equal to 11.64 meters. Okay? And so that means the offset, right? So the offset from the resultant force to the centroid, in this case, is only 0.09 meters. All right. Any questions on that? Okay. So very quickly, let's do part B for this problem, and then we'll take a break. Right? Okay. So part B. Right. So part B asks us to find the reaction force that's being applied by the stopper that's preventing this gate from opening. I had a mental typo, but two P's. Think about often. Okay. All right. So what does this mean, right? So because our pressure force here is slightly offset from the centroid, that's going to produce a moment around the hinge. And so in this case, our gate is hinged right at the centroid, right? And we know that to compute the moment, right, we compute the magnitude of the force multiplied by the perpendicular distance from that force to the centroid, okay? Which we have conveniently just computed up here, okay? Okay, so the moment from the pressure force is equal to the resultant force here multiplied by the distance to the hinge. Right? Which you can see kind of very clearly from the figure above. It's just 0.09 meters, right? That's how we compute moment. But if you were to put this in terms of the variables that we've already computed, the distance to the hinge is just going to be YR minus YC. Okay? So let's go ahead and compute that. Right, so we know FR is that 1,231,504. YR minus YC is 0.09. And so that gives us a moment of 110,835, bless you, 0.36 Newton meters. All right, and then if we look at the the gate here, right? When we look at the direction that the FR is pointing in, right? We can see just from the figure here that FR is producing a counterclockwise moment around that hinge. Right, you can say that this moment here is counterclockwise. Okay. So in order to counteract this, right, the stopper, which is being applied on the upper part of the gate, must counteract this moment. Okay, so to help us out with this, let's just draw a very, very quick free body diagram. Okay, so luckily for this, there's only two forces that we need to consider. All right, so we have our hinge. We have FR that's being applied right there, and we know that this distance from FR to the hinge is 0.09 meters. Okay. The stopper, right? So if we go all the way back to how our figure was drawn here, right? The stopper is this little wedge of material that's being applied on the top, right? And so that's going to apply a force, and so we'll call this F stop. That's going to be applied on the top part of the gate. Where the distance between the F stop, the reaction force, and the hinge, this is just going to be the diameter of the gate divided by T. Okay. Okay. So if we basically sum up the moments, right? So we basically do a summation of the moments around the hinge of this gate. Okay. We can basically solve for the magnitude of that stopping force. Okay. So we have FR multiplied by YR minus YC. Okay, so that's the moment that's being caused by the pressure force. We've already computed that. Okay, minus F stop multiplied by its moment arm, which is D divided by 2. All this is equal to 0. All right, so let's go ahead and plug in. So this quantity we can just plug in here. We move F stop times D over 2 to the other side, and we just multiply by D divided by 2. Okay. All right, so F stop is equal to, let's see, 2 over D times 110,835.36. Okay. All right, so let's go ahead and plug in for D. We know diameter here is 4 meters. Okay. So F stop here is just going to be 1/2 that. Okay, so F stop is 1/2 times 110,835.36, which I don't have in my head. So I will go ahead and do a calculator for that. 835.36 divided by 2, which is 55,417.68 newtons. All right. And so with that, let's go ahead and take a break. So when we come back, let's come back. I went a bit over. Let's come back 4:31. We'll go ahead and do one more example with hydrostatic forces, and then we'll finish off the day talking about buoyancy.
That is explode. Since you're using the same height, so it's not the same.
It's just zero. Or that same height. Oh,
If they slightly with the density of the liquids, what if you want, you're finding the height. For the height, you're finding the height. So for A,
what's your P1?
this liquid,
Wait, just
P2 is this liquid,
B. No.
and then the difference in pressure from A to B is still P. And then you just find your height. You want to find it. And this there's a different density. Steep.
All right, let's get back to it. Okay. All right, so we just finished our first example here with hydrostatic forces on surfaces. So basically, we took our inclined surface here, we computed the hydrostatic forces, and we did something somewhat useful for it. So we computed the reaction force. So this could be useful. Let's say in a situation you were designing this gate right here, and part of your design process is you were designing this stopper, right? So knowing that the stopper has to sustain a force of 55,000 newtons, that's not trivial. And so that's obviously going to affect the types of materials that you're going to choose for that stopper. It may influence the shape, right? But this at least kind of gives you a design point for designing the system. Okay, that's kind of why I changed the problem a little bit, just to kind of give you a sense of something useful you can do instead of just kind of walking through the motions and just computing the unit. Okay. So next example is kind of interesting as well. Kind of a more of a I would say kind of a theoretical situation, but kind of a really interesting one at the same time. Okay. Okay, so for this example here, let's consider a situation where we have two fluids, so one of them being water and another one being oil, and they're going to be separated by a gate. Okay. And the gate is square. Okay? All right, so our situation looks like this. And so on one side of the gate, we have water. Okay. So they're going to be separated. Right, so there's a wall here. The wall just comes all the way up to the surface of the water. Then right at the surface, there is a gate. So I know I'm drawing them with gaps here, but assume that there's no gaps. And so right now, just when the gate is closed, there's no leakage in between the two pools. Okay. But the gap is just there to kind of emphasize the fact that there is a gate there and it can rotate. Okay. So on the water side, we know kind of everything from there, right? So on the water side, we know exactly the depth. Okay. So we know that the depth from the top of the water down to the hinge, right? And just like the previous example, we're going to assume that the gate is hinged at the centroid. Okay, so we're going to assume that the depth here is going to be 1.5 meters. All right, and then on the other side, we have oil. but the oil is going to be at a different depth than the water. Okay? So we have this gate that's kind of preventing a kind of a catastrophe from going on. All right, so this on this side we have oil. Okay? But what we don't know is we don't know the depth of the oil, right? So there's going to be a distance from the top of the oil or the free surface of the oil down to the hinge. Okay, so we'll call this HO. But that is what we're going to be solving for. Okay, so that's going to be a mystery. We go ahead and draw our free surface indicators here. Other thing that we know is that we know the length of the gate here is 3 meters. Okay, so that we have a square gate which has a length or height of 3 meters and a depth of 3 meters. Okay, and even though I didn't say explicitly, but you can kind of see from the figure here, our gate here is vertical. So there's no incline here. So at least that's one thing we can simplify. Okay. So we know on the left-hand side, we know the specific weight of water. So the specific weight is just the product of the density of the fluid multiplied by the acceleration due to gravity. Okay. So on the left-hand side, we have the specific weight is 9,800 Newton per meter cubed. Okay. And on the right-hand side, the specific weight of the oil is 5,000 Newton per meter cubed. Okay. Okay. The other thing we know is that the gate is at equilibrium because there's no catastrophe, right? So there's no mixing of these fluids. Right. So assuming the gate is at equilibrium, what we want to do is we want to solve for the depth of the oil pool that's required to keep this system in equilibrium. Okay, so we're essentially going to be solving for HO. Okay. Okay. So pretty interesting situation, right? We have a gate that's preventing the mixing of these two fluids. Since these two fluids have a different density, have different specific weights, then in order to basically balance out the moments that are being caused by their hydrostatic pressure forces, then they need to be at two different depths. Okay, so basically we're going to be performing just like the part B of the last problem. We're going to be forming a sum of the moments and setting it equal to 0. We're going to have the water side contributing one part of the moment, the oil side contributing another part of the moment, and we're going to get an equation that we're going to use to solve for HO. Okay. All right. So let's start with that actually. So let's start with the free body diagram, just so we can kind of visualize everything that's going on. Never a bad idea to start with the free body diagram. All right, so we have our gate here. We have our hinge. Okay. On the left-hand side of the gate, we know that we're going to be acted on by the hydrostatic pressure force from water. Okay. And remember, just based on what we know about hydrostatic forces, it's going to be acting slightly below the centroid. Okay. I may have exaggerated that in this figure here, but we know it's slightly below. Okay. And so the moment arm, or in other words, the moment arm or the distance, the perpendicular distance between the force and the hinge, is going to be the difference between the center of pressure and the centroid. Okay. So this is going to be y r minus yc, okay, for the water. Okay, so just like the previous problem. And then on the oil side, we're going to have the same thing. We're going to have a force that's being applied in the opposite direction. We're going to call that FO. And that also is going to have a moment arm, where that moment arm is going to be YR minus YC for the oil. All right, and so if we sum up the moments, right, around the hinge, right, we have basically these two contributions, and they have to, even out exactly. Okay, so on the left-hand side, we have, let's see, so the water, let's go ahead and trace this around. Okay. Right, so based on the direction that the water hydrostatic force is going, we know the water is going to be producing a counterclockwise moment. Okay, and so the convention that I typically use is that counterclockwise moments are positive. Okay, so our water moment here is going to be FW times YR minus YC for W. Okay. Positive. And then the contribution from the oil is a clockwise moment, because it has to be, otherwise there's no balance, right? So that can be a minus FO times YR minus YC for the oil. And all this is equal to 0. Okay, so that's our master equation here. So that's the equation that we're going to use ultimately to solve for the depth of the oil. Okay. Now everything from the oil we can't compute yet, just because we don't know the depth, but we can compute everything on the water side. So let's compute everything on the water side, just because we know the depth, we know the size of our surface, we know the density of the water, the specific weight. So let's compute everything on that side first. Okay. All right, so just like before, we're going to need to compute the magnitude of the pressure force as well as its center of pressure, the location. Okay, so let's start with the magnitude. So magnitude, remember, is quite simple, right? So we have the rho of the water times gravity times HC times the area. So in this problem here, we aren't given the density of water, although you could easily compute it. We're given its specific weight. So remember, specific weight is just the product of density times gravity. All right, so we plug everything in here. We know HC. HC is just 1.5. Okay. And so with everything plugged in here and the area here is 3 times 3 meters square. Right? Because remember, we have a square gate. And so since we know the height of the gate, we also know its depth, which is also going to be 3. HC here is 1.5 meters. That's given to us in the problem. Then we know that FW here is 132,300 newtons. Good. Okay, now let's compute the center of pressure on the water side. Okay. Okay, so let's go ahead and write in our formula for this. And so we have the moment of inertia with respect to the centroid, right? So we're going to look that up for a square. divided by YC times A plus YC. Okay. Okay, so just like we did in the previous problem, let's go ahead and plug in everything here. Let's start with YC. Okay. So remember, YC is the distance to the centroid along the inclined path. Okay. But in this case, our surface is vertical, right? And so our inclined path, or our angle, I guess you could say, is 90 degrees actually. Okay. So for vertical surface, theta is 90 degrees. Okay. And so if we plug that into our formula, YC equal to HC divided by sine theta. Right, so sine theta, sine of 90 is just 1. So in this case, we get YC is just equal to HC. Okay. The other thing that we need here is the moment of inertia for a square. Okay. So this is something you can look up in the table as well. Right, so from a table. And when I say table, I think there's probably one in the textbook, but I think, you probably can search for one. Right, so just search up a table for moment of inertias for specific shapes. Okay. Right, so for a square, the moment of inertia with respect to the centroid is 1/12 times the side length to the fourth power. Okay. Right, so we plug in for that. We know the side length in this case is 3. Right, so we have 3 raised to the fourth power divided by 12. And so that gives us 6.75 meters to the fourth. Okay. So let's go ahead and plug in for that. So we plug in for all of this. Okay. We plug in HC is equal to 1.5. We plug in our moment of inertia of 6.75. We plug in our area of 9. Right, and what we get is 2 meters. All right, and so that lets us compute everything on the left-hand side of that equation, right? So left-hand side of this equation, we have the magnitude of the water force multiplied by the difference YR minus YC, okay? We know YC in this case is 1.5 because it's the same as HC. And so that means the total moment, FW, multiplied by YR minus YC, water, is equal to 132,300 multiplied by 2 minus 1.5 equal to. Okay. By the way, I know there's a mistake in the notes, and so this is a this is a corrected version of the example in the notes. Okay. Okay, so we basically have that. And so what we get from this is 132,300 divided by 2, which is 66,150 Newton meters. Okay, so that's the total moment that's resulting from the left-hand side, okay, from the water side. So that means that our moment from the oil has to match that moment. Okay, so let's compute everything on the oil side. But of course, everything on the oil side will have to leave in terms of the unknown depth, right? So that'll be the variable that we're going to solve. Okay, so for the oil side, we're going to do the same thing. So let's go first compute the magnitude of the pressure force from the oil side. Okay. So once again, this is going to be rho of the oil times gravity times H oil times A. Okay. Right, HO is unknown though, so we're just going to leave it as an unknown variable. Let's go ahead and plug in, right? So the rho times G here, this is the same as the specific weight, which we are given in the problem is 5,000 newtons per meter cubed. And the area we know is 9 meters square. Okay. And so we plug all this in, we get FO is equal to 45,000 HO. Okay. HO being unknown. Okay. Now we need its center of pressure. Okay. The center of pressure, same formula. So we have YR is equal to IXC divided by HO times A plus HO. Okay, so let's go ahead and plug everything in for this as well, right? So remember, HO is still unknown, but we can still plug in for everything else, okay? So IXC, that's going to be exactly the same because our gate is still the same, right? So IXC here is 112 times the length to the fourth power, okay? So that's still 6.75 meters to the fourth, okay? Area here is 9 meters square. HO is unknown, okay? Just verify something real quick. Okay, so we put all this in, we get 3 over 4 HO plus HO. Okay. All right. And so let's go ahead and take the product of these two. So we have FO times YR minus YC of the oil. Right. And so we do that, we get 45,000 HO multiplied by 3/4 HO plus HO minus HO. Okay, because HO, that is the location of the centroid, okay, for the vertical gate. Okay. There's a glitch in the matrix because everything HO is canceling out of everything. Let me just go ahead and just double check that really quick. That, that's not right. Let me just check something. So I thought I noticed a typo in my notes, but I think I had it right. I think I had it right the first time. I apologize. Okay. Let me kind of go back up here and fix this here. Okay. So the moment here. Oh, interesting. Okay. All right. So actually, so the moment here, we're actually not going to subtract the centroid here. We're just going to subtract. We're just going to multiply it by the center of pressure. Okay. All right. So we have FO here multiplied by YR. So that's going to give us an expression that does still have HO, right? So we have 45,000 HO multiplied by 3 over 4 HO plus HO. Okay. Right, so we multiply that through, and what we get is we get 33,750. The HOs are going to cancel out on that first term, and then plus 45,000 HO squared. Okay. Now this must equal the same moment that's given by the water. Okay. Okay. But for the water, we have to do the same correction. So for the water, we're just going to multiply the product of the magnitude of the force multiplied by the center of pressure. Okay. So we have our moment equation. Right? So this is a corrected version of kind of what I had earlier. Okay. So the moment equation is going to be product of F water times the center of pressure for the water minus F oil minus center of pressure for the oil, and that's going to be equal to 0. Okay. I apologize. Yeah, I know beginning of this problem is a little bit confusing, but you know, this will be the corrected version here. Okay. Okay. So the product of the oil force multiplied by the center of pressure, that's going to be this quantity here. So we're just going to plug in for that. Okay. All right, so let's go ahead and plug in for that right now. So we have 33,750 plus 45,000 HO squared equals 0. Okay. And then for the water, we're just going to go ahead and multiply kind of our two quantities from earlier. Okay. So we have the force, the pressure force from the water. Pressure force is 132,300 newtons multiplied by center of pressure, which is 2 meters. Okay. Okay. All right, so this is going to give us an equation that we can use to solve for HO. Okay, because if we multiply these two things together, we get 264,600 minus 33,750 plus 45,000 HO squared equal to 0. Okay. Let's go ahead and perform that arithmetic. So we can go ahead and do the subtraction of 264,600 minus 33,750. That's going to give us 230,850. Okay. And then that's going to be minus 45,000 HO squared, okay, is equal to 0. I forgot the parentheses when we were plugging in for FO. Okay, otherwise you get square root of a negative number, which is not good. Okay. Okay, so then we kind of do a little bit more arithmetic here. We get HO squared is equal to 230,850 divided by 45,000. And so we get HO squared, we do that arithmetic, is equal to 5.13. Okay. Right, and then finally, all we have to do to solve this is just we take the square root of both sides. And so square root of both sides, we get HO is equal to 2.265 meters. I apologize for the confusion for this one. This one still doesn't sit super right with me, so I'm going to go double check this in my office when I have a bit more time, and I will send out a revised version of this this example. But hopefully with this example, at the very least, what I wanted you to get from this example was just a little bit more practice, computing the hydrostatic pressure force as well as the center of pressure. But what's unique about this problem is that, we did this for a vertical surface, okay? So you can see for a vertical surface, it's a little bit more straightforward because you don't have to worry about the incline angle. You can just set the YC is equal to H. Okay, so that was kind of the main thing with this example that I wanted to show with you guys is that, if you have a vertical surface, it's a little bit easier. And also just kind of seeing more calculations of this, I think is just a bit more. All right, any questions on this example here? Yes.
So we found were we trying to find the height of the oil from free space to the centroid?
Exactly.
So when we did FW times Y of R and we multiplied by 2, when we just multiplied by half the length of the beam then in order to find the centroid?
So the 2 there was the center of pressure for the water, and so that's the depth from the free surface of the water to where that pressure force is located.
Okay, so that pressure force isn't at the resultant, then it would be at the centroid?
No, it's at the center of pressure, which is slightly below the centroid.
Okay.
Yeah, that's the part that's confusing to me because normally when you compute the sum of moments, you have to do it around the same hinge.
Yeah.
But for some reason, the way I have this example here, I have different moment arms, and so that's kind of why I kind of started the problem the way I did was I subtracted the center of pressure from the centroid.
I thought that made more sense.
Right. But then when you do that, you kind of cancel out the HO. So I'm gonna take a look at this example a bit more. And I'm gonna draft up kind of a revised version of this example. I'll send it to everyone after class today. So I apologize. Yeah, it's a little bit confusing. All right. Any other questions on this example here? Okay. All right. So one more point here, one more topic before we get to buoyancy. Buoyancy you'll see is quite simple. Okay. Let's talk about hydrostatic forces on curved surfaces. Okay. So, the last 2 examples that we did showed us how to compute the hydrostatic force on a planar surface. Okay. But, in a lot of situations, and actually this is actually very common in reality, whenever you have a pool or a container of liquid, right, whether it be from like a water bottle to a very large container of water, right, you're always going to have some curved surface at the bottom. So there's always going to be some kind of filling. Okay. And so usually, whenever you have a liquid like this, right, and it's in some kind of container, right, you'll almost never see a container of liquid that has kind of a sharp angle or a 90-degree corner at the bottom. There's always going to be some degree of kind of curvature at the bottom, right? And the reason for that is that it's just a much more stable shape. It kind of prevents any kind of stress accumulation that can build up. Okay, if you've taken kind of a solid mechanics or a structures class, you'll know that sharp corners, sharp angles are kind of the enemy of stability and good design. Okay, so there's always going to be some kind of curved surfaces. Okay? Now, the issue though is that, a curved surface doesn't exactly fit with the kind of the algorithm or kind of the methodology that we just went over. Okay. But, if you're designing these kinds of systems, you want to know, what is the pressure force that's being applied onto this surface? So how can we apply what we just learned on hydrostatic surfaces, hydrostatic forces on planar surfaces, and how can we apply that to curved surfaces? Okay. All right. So the trick to doing this actually is to kind of isolate a section of fluid that contains the curved surface, and then kind of doing a summation of forces, where from the summation of forces, we can then compute the resultant pressure force. Okay. So the methodology works like the following. So let's say we have, I'm going to draw kind of a bigger kind of example here. Okay. So let's say we have a curved surface, and it's a surface that's submerged under a fluid. Okay. So what we're going to do is say that, our curved surface kind of goes from here to maybe about here, right? And then from those points on, we have a kind of a perfectly horizontal surface and a perfectly vertical surface. Okay? Let's kind of use these as our guide marks. And so let's go ahead and kind of take some theoretical scissors and kind of cut out a section of the fluid here. All right, so let's go ahead and pull that over here. All right, so now we have a surface that looks like the following. Or I should say a section of fluid that looks like the following. Okay. All right, so here we have our surface in question, right? So this is the surface where we want to compute the forces on. But we know that the surface here has to be in static equilibrium, right? And so let's go ahead and add in some additional forces here. Okay. First of all, right, since we're isolating a section of fluid, our fluid here is going to have some weight. So the W there is the weight of the contained fluid. Okay. Next. Okay. Next, we have the hydrostatic force of all the fluid that's above this section. Okay. We'll call that F1. Right? Because that's going to be exerting a pressure force onto our theoretical section here. Okay. Next, we have F2, right? So F2 is going to be the hydrostatic force that's being applied on that vertical surface. Right? So those are all the forces that's being exerted by the fluid. Okay. But in order to keep this section in equilibrium, we're going to have some reaction forces that are being applied from the wall. Okay. And so we can break up those reaction forces into two different components. So we can have a vertical component and a horizontal component, just for the sake of convenience, right? So you kind of see it. Okay. So we'll have FV. Okay. So FV is going to be the vertical component of the reaction force from the wall. Okay. And we'll have FH, which is the horizontal component of the reaction force from the wall. And so the idea here is that if we can compute the reaction forces from the wall, we know that the reaction forces are an equal and opposite reaction to the hydrostatic forces on that curved surface, right? And so the reaction force that we compute is going to be exactly the same as the hydrostatic force on that curved surface. Okay? And so if you can take this kind of theoretical slice of your fluid and solve for FH and FV, right, that's going to give you your hydrostatic forces on that curved surface. Okay? Now, this may seem a little bit complicated, but if you think about it, you have basically the weight of the fluid. The weight is usually pretty straightforward to compute. That's just the density of the fluid multiplied by gravity, multiplied by the volume of fluid that's contained. That's pretty straightforward. We have a hydrostatic pressure force on a horizontal surface, so that's F1. We know that's easy to compute as well. And then we have the hydrostatic pressure force from a vertical surface, F2, which also we know how to compute. Okay. Now, the best thing about this is that, there's no need to compute any moments here. Okay. And so there's going to be no need to actually compute any centers of pressure. Which is kind of the hard part. So actually, you can solve these problems just by doing simple sum of forces. Okay, so let's do a very quick example just to kind of showcase this thing. Okay, so let's consider the flow of a fluid, or let's consider a fluid that's half filled within a cylindrical tank. Okay, we have our cylindrical tank here. It's going into the page. Okay, it's half filled, and so it's going to be only halfway filled, just like this. Okay. Let's say the diameter of this pipe here is 2 meters. Okay. Okay. And so in this situation, we want to compute the total amount of hydrostatic force that's being applied on the entirety of the cylindrical base. So basically, we want to compute the hydrostatic pressure force on this entire bottom half, just like that. Okay. And then let's also assume that the length of the tank is 3 meters into the range. Okay. Okay. All right, so to do this, we're going to apply the methodology that we did up there. Okay, but in order to make it tenable, right? So even though the problem asks us to compute the entirety of the bottom half, right? We kind of have to split this in two. Otherwise, we wouldn't be able to actually solve this. So actually, to compute this, we're actually going to take just a quarter slice, just like this. We're going to take the result from the quarter slice and then just multiply it by 2, because otherwise we kind of need that vertical surface there. Otherwise, it'd be very hard to compute the pressure forces. Okay. Because if you took the entirety of the bottom half, right, you took that as the entire closed surface, then it's going to be a bit more complicated to do so. Okay. Okay. All right, so let's go ahead and take a look. So let's go ahead and take this slice, and just like we did up there, let's go ahead and put in the weight of the fluid. Okay. We have F1, F2, FV, and FH. Okay. Right, and so the goal here is to solve for FV and FH. Okay. Okay. All right. So if we solve for, let's do a sum of the forces in the y direction first. All right. So basically, we're going to do a sum of the forces in the y direction, some of the forces in the x direction. So that's going to give us FV and FH. Okay. So some of the forces in the y direction we have FV minus F1 minus W is equal to 0. Okay. That's just all the forces in the vertical direction. All right. So in this particular case here, we make the note that if we look at the horizontal surface or the surface where F1 is applied, that actually coincides with the free surface, right? Right, and we know the free surface has a pressure of 0. So actually, in this case, F1 is equal to 0. Okay, so we're just going to go ahead and cancel that guy out. Okay, so then all we need here is just the weight of the fluid. Okay. All right, so weight of the fluid here is just going to be the specific weight of the water multiplied by the volume that it occupies. Okay. Right, so we're taking the volume of a quarter of a cylinder, right? So we know the depth of the cylinder, we know its diameter. The diameter is 2. Okay. All right, so the volume in this case is going to be the area of the quarter cylinder multiplied by the length. Okay. So the area of the quarter cylinder is going to be pi r squared divided by 4 times the length. Okay. Where r here, the radius here is if the diameter is 2 meters, then the radius is 1 meter. Okay, so this can be pi over 4 times 1 meter squared times the length, which is 3 meters. We multiply that by the specific weight of the water. Specific weight of the water is 9,800 Newton per meter cubed. Okay. And so we plug all that in, you get the weight of the water contained in that quarter slice is 23,090.71 newtons. Okay. All right, and so that tells us that the vertical force FV, right? The only other contribution in the vertical direction is the weight. So we have FV has to equal W. So that means FV must equal to 23,090.71 newtons. Okay. All right, any questions on how we got that result there? Okay. All right, so now let's do the horizontal forces. Okay, so the horizontal forces, we have F, some of the forces in the X direction. Okay. We only have two contributions here. We have F1, okay, or excuse me, F2. F2 and then minus FH is equal to 0. Okay. For F2 here is going to be the hydrostatic force on a vertical surface. Okay. Okay, so we know how to compute this, and so we have F2 is equal to specific weight of the water multiplied by the height of the centroid multiplied by the area. Okay. Specific weight of the water is 9,800 Newton per meter cubed. Height of the centroid here, so we have basically a vertical surface, right? Where the length of that vertical surface is 1 meter, right? Because it's basically half the diameter, which is 2, right? And then the centroid is going to be halfway along that. So the centroid is going to be at 0.5 meter. And then the area of the surface here is going to be the radius multiplied by the depth. Okay. So we have a rectangle, we basically have a rectangular surface. You have 1 meter times 3 meter, which is the depth. Okay. Okay. Right, so we put all that in, we just punch into a calculator, we get the hydrostatic force on that vertical surface is equal to 14,700 newtons. Okay. Which by our force balance here must also equal FH as well. Okay, so FH, the horizontal force, has to equal 14,700. All right, so now that we know both components of that reaction force, let's go ahead and combine them. Okay, so the resultant force is basically we're just going to take the magnitude of these two components. Okay, so finally we can compute the resultant force. Okay. So Fr in this case is we have the vertical component Fv, we have the horizontal component Fh. Okay. Resultant force is just going to be the magnitude of both. Okay. So this is going to be square root Fh quantity squared plus Fv quantity squared. Okay. Right, we have our simple kind of distance formula or simple magnitude formula for a vector. Okay, so we plug all this in, we get 27,372.81 newtons. All right. Any questions on that example there? Okay. All right. And so last topic that we're going to go over, this is going to help you out for problem 5 on the homework, is buoyancy. All right. Buoyancy is kind of the fun one because we're talking about hot air balloons and fool's gold and things like that. Okay. So I saved a good topic for last. I know that the last topic was kind of intense. Okay. So when we're talking about buoyancy, we're talking about situations when you have a body, right, or a volume that's submerged in a liquid. Okay, there's going to be a natural force that kind of pushes the object upwards. So whenever you have a body or some kind of volume or object that gets submerged in a fluid, there's going to be an upward force, right? So this gives rise to the notion of flotation, right? And so I think intuitively, we know that if you take an object, you put it in water, you put it in some kind of fluid, some objects will float and some objects will not. It's interesting. My parents recently have retired, so they've kind of served their corporate overlords long enough, and they decided to retire. They've been traveling a lot, and so recently they went to the Dead Sea. And my mom, who is deathly afraid of water just because she doesn't know how to swim, she had a great time in the Dead Sea because the Dead Sea is actually so salty. It has so much salt in it that density of the water there is huge. So you don't need any kind of life jacket. You don't need any kind of flotation device. You just step into the Dead Sea and you just kind of float just on your own, which is fascinating. And so that's kind of a good segue to talking about kind of what we're talking about here. Okay, because the amount of force, the amount of buoyant force that gets applied onto the body is dependent on two things. And so it's dependent on the amount of basically the volume of whatever you are trying to float and the density of the fluid that you're trying to that you're floating in. Okay? And so that gives rise to what's known as Archimedes' principle. You probably heard of this before. Okay? So Archimedes' principle is the kind of the whole idea of flotation, where basically saying that the magnitude of the buoyant force. Right? So you put an object in a liquid, there's going to be an upward force. The magnitude of that force is going to be equal to the weight of the displaced fluid, of the weight of the fluid displaced by the object. All right, so FB equal to, okay. We have the specific weight of the fluid multiplied by the volume displaced. Now, I worded that very carefully because, volume displaced, the way when you say that, we're basically saying whatever portion of your object is underneath the water. Okay. So if you have an object that's not completely submerged, right, and so only part of it is actually above the water, that volume displaced is just whatever portion of your object is underneath the surface of the lake. So when I say volume displaced, this is the volume of submerged portion. All right, so if you're completely submerged, then then the volume displaced is just the volume of your object. But if if you're only partially submerged, then it's only, you only just compute the volume of whatever is submerged there. Okay. Okay. Now, where this where this kind of gets interesting is that this upward buoyant force is always acting in competition with the weight of the object. Okay. Because the buoyant force will be applying an upward force, but the weight is going to be applying a downward force. So these two things are competing. Okay? And so the weight of an object, okay, is equal to its specific weight. Okay? Now be careful here, right? So I'm using specific weights for both, but this specific weight here for the weight is the specific weight of your object. Multiplied by the volume. Okay. But the weight of the object doesn't care whether you're submerged or not, right? So the weight is the weight. And so when I say V here, this is the total volume of your object. Okay. So these two are kind of complete opposite, and they're always going in the same direction, but one is negative and one is positive. Okay. So when you sum the forces, okay, well, for this one, let's assume that we have a completely submerged object. Okay. We take the sum of the forces in the y direction. Right, so we're going to have our buoyant force going in the positive direction and the weight in the negative direction. Okay, so that's going to be equal to 0. Okay, let's plug in. Right, we plug in for this. We have the specific weight of the fluid multiplied by the volume minus the specific weight of the object multiplied by the volume. Okay. Our volumes here are going to cancel out. And so this is telling us that, if we have an object that's completely submerged, if the sum of the forces is equal to zero, that means that only happens if the specific weights of the object and the fluid are same. In fact, we can kind of extrapolate kind of mentally a little bit too, where if the specific weight of the fluid is greater than or equal to the specific weight of the object, right? Then there's going to be at least a net upward force of zero. But if if the fluid is much more dense, then you have an even greater upward force. Okay. But if there is a net downward force, right? If there's a net downward force, then your object is going to sink, right? So that occurs if the specific weight of the fluid is less than the specific weight of the object. Okay, so if your object is more dense or has a higher density or a higher specific weight than your fluid, then you're going to sink in that fluid. Okay. So this is probably the form of Archimedes' principle that you probably have learned maybe in like your 8th grade science class, right? So I think the story that's typically told is that, kind of old school jewelers used to use Archimedes' principle to determine whether you have fool's gold. So kind of during the gold rush, there was a time when people try to make a lot of money off selling gold, but people found a particular substance that shines very similarly to gold. So they try to pass that off and sell it as if it were real. But real gold is actually very dense. It's a very dense material. So if you put it in water, it just sinks to the bottom very quickly. But fool's gold was made of a material that was not dense at all. And so if you put it in water, then it'll actually float. And so people use that test to determine whether you have a real gold. Okay. All right. Any questions on this? Yes.
Where's that subscript say? Right after the FY.
FY, FB, buoyant force. You're talking about this one right there, right?
Yeah.
Yeah. Mhm. Okay. All right. So let's do an example very quickly. I want to make sure I get through this before the end of class today. Okay, so let's use this idea of buoyancy to talk about life jacket design. Okay. So let's say that you are working for a sports equipment company and you are designing a new life jacket. Okay. All right. So per U.S. Coast Guard regulations, okay. So per U.S. Coast Guard regulation, a life jacket should be able to cause at least a 22-pound weight to float. Okay. All right, so the way life jackets typically work is that they're made, you basically construct them of some kind of foam material that has a very, very low density. Okay, so for this particular case, let's say that we are using a material, or we're using a foam that has a specific weight of 2 pounds per feet cubed. Okay. So we are working with English units here, so it's a little bit of a transition from our SI. Okay. Okay. And so in addition to the foam, so a life jacket just can't be completely foam. It has to be encased so the foam doesn't get wet. There's also, straps and buckles and things like that. And so let's say that, for this particular life jacket, all the other remaining components of the life jacket have a net weight of 1.3 pounds. Okay. All right. So with all this in mind, right? So knowing the amount of weight that it should support, let's compute. Let's compute the volume of foam that's needed in order to satisfy all of these requirements. Okay. So the idea here is that basically the more foam that you include, the more buoyant or the more life-saving this life jacket's going to be. Okay. But generally speaking, whenever you're designing a product, the more volume or the more stuff you put into it, the more it's going to cost to produce, right? And so a lot of times, you're going to be tasked if you're going to be in product design, what's the least amount of material, what's the least amount of stuff that we can include in order to sell this product as it's designed. Okay. All right, so let's take all this information and let's incorporate it into a free body diagram. Okay, so let's say we have our life jacket and it is a stunning shape of a rectangle. Okay. Right, so let's say that we have, right, so on this rectangle, we are going to be supporting the weight of our person. Right, so remember this weight is 22 pounds as dictated by the Coast Guard regulations. Okay. We have the weight of the other stuff, so I'll call it FS. Right, so the other stuff is going to have a weight of 1.3 pounds. Okay. We're going to assume that the stuff has a negligible buoyant weight. So we're going to say or assume that their density is very close to water. All right, we have the buoyant force. And so the buoyant force here, of course, is going to be the volume of our life jacket multiplied by the density or the specific weight of the fluid, right? So in this case, our fluid is water. Okay. Right, so of course, one thing we need for this problem is we need to know the specific weight of water in English units, which I will give you. Okay, volume is what we're solving for. We have one last component to our free body diagram here, which is the weight of the foam, right? So the foam itself is going to have some weight, which remember is always going to counterbalance the buoyant force. Okay. And so the weight of the foam here is going to be the specific weight of the foam multiplied by the volume. All right, so that gives us everything we need. And so, luckily for us, all of these forces are in the vertical direction. And so we only need to sum forces in the y direction. Okay, so we sum all the forces in the y direction. We have buoyant force minus weight of the foam minus weight of the person minus weight of the stuff. Okay, all that is equal to 0. All right, so this is just a very simple kind of just plug and chug type problem. And so we have expressions for everything here. So I'm going to skip a few steps, but I'm going to get to kind of the final result. Okay. So after you do some plugging and chugging and just algebraic manipulations, you should get volume of the life jackets equal to 22 pounds plus the 1.3 pounds divided by the difference between the specific weight of the fluid minus specific weight of the foam. Okay. All right. So in order to complete this, we of course need the specific weight of water in English units, which is 64 pound per feet cubed. Okay. We know from the problem that the specific weight of the foam is 2 pound per feet cubed. Okay. All right, so we have a big delta there, so we have a big difference. Right, and so we plug everything in, we get the volume that's needed is 0.376 feet cubed. All right, any questions on that example there? Okay, one last point, just so that I know there's a question on this on the homework. Let's talk about buoyancy stability. I apologize for kind of rushing this. The first example we did after the break kind of threw me off a bit. So all this is detailed in more detail in the notes, but I at least want to mention just the main points, just so that we can at least answer that question on homework. Okay. Okay. All right. So we've computed the magnitude of the buoyant force, right? So we know how to compute that. But what about the location, right? So the location of the buoyant force is actually quite simple. The location of the buoyant force is going to occur at the centroid of whatever portion is submerged under the liquid. Okay. So whatever portion of your object is submerged under the liquid, that the centroid of that is going to be where the buoyant force is located. Okay. Now, an interesting interesting kind of phenomenon happens when you compare the location of the buoyant force versus the center of gravity of the object's weight. Okay. Right, and there's really kind of two scenarios. So there's a scenario where the buoyant force is located above the center of gravity, and there's a case where the buoyant force is located beneath the center of gravity. Okay. The center of gravity, of course, is where we apply the resultant force of the weight. Okay, so I'm just going to draw them and just kind of talk through them just for the sake of time. Okay. So whether one is above or below is actually important just because of the directions in which they act. Okay. Now, if we look at a situation where the buoyant force is above, right, we call this a stable situation. Because what happens if you try to perturb this, right? And by perturb, what I mean is, let's say that you try to rotate it a little bit by your hand, right? If you look at the locations or where those forces are acting, right, the weight force and the buoyant force are actually trying to kind of reposition the object from where it was before. right? Just because the weight force is pulling down, the buoyant force is pulling up. Okay. Whereas if you have the other case, we call this actually an unstable situation, right? Because if you rotate the object a little bit, the buoyant force is going to want to pull the bottom of the object upwards, and the weight is going to want to pull the top of the object down below. Okay. So we call that an unstable position because if you perturb it a little bit, then it'll actually change orientation very dramatically. Okay. Okay, so that's kind of the main thing with stability. So I think that hopefully should be enough for you to answer the question on. Okay. Any final questions before we wrap it up for the week? Okay, all right. So thank you guys for coming this week. I know it was a very intense week. We covered basically 3 weeks of fluids in 3 days, and so I know it's a lot of information. Definitely get started on the homework if you haven't done so already. I'll be available over email tomorrow. If you have questions on the homework, don't be afraid to send me an email. I will do my best to answer you. If not, hope you guys have a good weekend, and I will see you guys next Tuesday.
Good job.
Yeah, so we'll go over the format of the exam next week, but it's going to be formatted similar to the homework. So there's going to be a conceptual portion where I'm asking you to do like 4 short answer questions. So you can answer those. And then there will be a problem solving portion. There will be problems that are similar to the example, similar to the homework. There's probably all 3 of those. Okay.
And we're gonna do a review.
I'll give you a study guide, but I don't think we'll have time for an explicit. Yep.